Today we would like to introduce the example application of our rmNVMe-IP Core by Design Gateway. This video is the second part of the rmNVMe-IP Core video. Please check the first part of the description below for more understanding. Let's see the example applications that can be accelerated performance by our rmNVMe-IP Core. First, the application is a write or read-intensive application. For write-intensive applications, the write buffer size is typically set to a large value while the read buffer size is kept small to optimize resources. However, for read-intensive applications, the read buffer size is increased to prioritize high read performance. Our rmNVMe-IP support configurable buffer size for both write and read to achieve optimum performance in your application. In the case of mixed-use applications, a moderate size is applied to both the write and read buffers to achieve a balanced read and write performance. Second, the application is multi-channel data acquisition. The key feature of our rmNVMe-IP is allowed to execute multiple read and write commands simultaneously. Our rmNVMe-IP can be adapted to the system that requires multiple user access to a single SSD simultaneously at maximum possible performance without CPU invention. One example of such kind of a system is a multi-channel data acquisition application. This presentation shows an example scenario for 4 high-speed write users and 1 slow-speed read user. The system integrates multiple data sources through switch logic. This switch logic divides the data received from the different sources into 4 kilobyte blocks and sends multiple 4 kilobyte write requests to our rmNVMe-IP. The read command is periodically requested at a slower speed to maintain system monitoring. However, the read speed is deliberately limited to preserve high performance in the write interface. As a result, write speeds of 6,000 megabytes per second or 1,500 megabytes per second per channel for 4 users can be achieved when the read speed is less than 300 megabytes per second. Third, the example application is a high-speed file system. Typically, the file system device driver in an operating system must support 2 key features to ensure efficient data storage and retrieval. Firstly, the file system must support random access. This allows for data to be split into small blocks and stored in different areas of the storage, maximizing the utilization of available storage space. Secondly, the file system must support concurrent write and read commands. The file system consists of a file table and user data. While transferring the user data, the file table must be monitored and updated. And most importantly, our rmNVMe-IP Core can fully handle NVMe protocol internally without CPU or OS. As a result, the file system can be accessed and updated with high efficiency by supporting concurrent write and read operations. The rmNVMe-IP is designed to support simultaneous write and read commands at high speed performance. Up to 3,000 megabytes per second for mixed write-read command, the high-performance file system by our rmNVMe-IP provides a reliable and efficient solution for data storage in both embedded systems and high-performance computing systems. And the last example application in this video is multithreading for database server. The FPGA can be utilized as the offload engine for the storage server to access physical disks like NVMe SSD storage. In large-scale systems, multiple threads frequently access the storage, leading to a high volume of read and write requests being sent to the CPU. The write data, which is usually large, is stored in the main memory. The FPGA platform's PCIe engine provides an interface that allows the offload engine to receive command requests from the CPU and directly access the data in the main memory with high performance. The file offload engine sends read and write requests to the rmNVMe-IP via the read command interface and write command interface, respectively. All write data is transferred via the write data interface and stored in the NVMe SSD. The read data from the NVMe SSD is returned to the file offload engine via the read data interface and finally, returned to the thread through the main memory. By implementing this kind of hardware system, storage server access can be accelerated with high performance while requiring fewer CPU resources. Hope this second part video can help you see the opportunity and potential of our rmNVMe-IP Core in real-world applications. Part 3 for the demo and performance will coming soon. For more technical detail, Please visit our website designgateway.com or just click the link in the description below. Thank you for watching and see you in the next video.